Hello, we're going to go over chapter 19, which I've abbreviated quite a bit. Basically talking about entropy and the Gibbs free energy overall, all right? Entropy is denoted with a capital S, all right? Sorry, I injured my shoulder, so it's kind of hard to reach up and write. But anyway, our entropy is a thermodynamic quantity that measures disorder, basically. Disorder or randomness of a system. Actually, I'm not sure this is going to work out. My shoulder, it's hurting quite a bit. Basically, the more disordered or random the system is, the larger the value of S. Okay? We're going to see that delta S, the change in entropy, which I told you before, delta is the change in, is going to be entropy final minus entropy initial. Okay? So if delta S is greater than 0, entropy has increased. If delta S is less than 0, it's negative, entropy has decreased. So entropy has increased. What does that mean? It means it's become more disordered, is what it means. Okay, so for example, if you clean up your room, put your clothes away into the drawers, everything's washed, you swept, vacuumed, whatever, made your bed. Okay, what happened? You've decreased your entropy, okay? You've decreased the entropy of your room. Now, you did that, say, on Monday. Now come Friday, what happened? You haven't been keeping everything clean, you got clothes laying around, you haven't vacuumed, you haven't dusted, your clothes is dirty. What happened? Your entropy of your room has increased, okay? That's a simplistic example. Let me go into a little bit more detail about entropy. If we were having a regular class, I'd go into quite a lot more detail, but since we're just doing this lecture, I'll just talk about it a little bit. First of all, in any real-world process, entropy always increases, okay? Entropy always increases, right? So in the example of where you cleaned up your room and you decreased the entropy of the room, right? You did your laundry, you folded your clothes, you put it away, blah, blah, blah. So the entropy of your room decreased. However, what had to happen? You had to work to decrease that entropy, okay? The work that you did to decrease that entropy, the work that you did increased the entropy overall. So even though you decreased the entropy of the room, in say for the universe, you've increased the amount of entropy, right? Now this is going to be for any real world process, entropy will increase overall. Again, you may decrease the entropy of a system, but the entropy of the universe will increase overall. All right? Our entropy, just again a little bit more, our entropy is based on the number of states available for that particular system, okay? So, for example, let's take a look at a deck of cards. So you have a deck of cards, right? There's 52 cards. You have them arranged, right, through the numbers, 2 through 10, then Jack, Queen, King. Okay, you have each of the suits. So there's only 4 suits, right? Now, you have those 4 suits. You're going to keep those parts ordered, 2 through, again, the King. Well, I guess include the Joker, whatever. You're going to have those are ordered, right? So there's only a certain number of ways to order those. You have 4 different things. The actual number is, using permutations, I'm not going to get into that, it'd be 24. You'd have 24 ways to order it, okay? With, say, spades, hearts, whatever it might be, all right? 24 different ways to order those, right? Now, You're going to take that deck and you're just going to shuffle it. You're going to split it in half, shuffle it several times. If it's not ordered like that, let me write this on the board. So again, when it's ordered, 2 through the king, okay, then you can mix up the 4 different suits though. You're going to have an ordered deck. It's actually n to the permutation, so 4 to the n, which is equal to 24 different states, 24 different ways to order the suits, the 4 suits, okay? You're keeping the 2 through king the same. Now, if you're going to disorder your deck, okay, you have 52 cards. You're mixing them all up now. Again, you're going to have n permutations. You're going to have 52 to the n factorial. That's a factorial, sorry. N factorial is what that is. N factorial. You're going to end up with, it's approximately 8 times 10 to the 67 different ways to order that deck when you shuffle it. Okay? 8 times 10 to the 67. That's a huge bleeping number, right? 24 or 8 times 10 to the 67. So now, you're going to go randomly pick up a deck that's been used, and you're shuffling it. Now, as you're shuffling it, what are the chances you think that you're going to end up with one of those states, or one of those states? You're going to end up with ordered random shuffling. You're going to end up with that, or you're going to end up with one of these. You're going to end up with one of these. You can spend several lifetimes shuffling your deck to try to get, randomly shuffling to get an ordered deck. Not going to happen. Why? Because there's 8 times 10 to the 67 ways to have an unordered deck. Okay? Now the reason I'm telling you this is how entropy is based on. It's the amount of disorder, but basically the more disordered your system, the more states are possible. I hope that kind of makes sense, right? I'm just trying to give some background for this. I'm not going to ask you to explain this or something. But so in general, entropy increases when liquids or solutions are formed. So let me write this on the board again. Actually, let me draw this figure. Let me draw this figure and we'll talk about this right here. So I'm going to put entropy here on the y-axis. Down here, I'm going to have the temperature. The entropy is related to the temperature. The higher, or it can be, okay? We're not going to have the temperature. Generally, the higher the temperature, the greater the entropy, right? So here, down here, we're at 0 for both, okay? This is 0 Kelvin. And we're going to end up with this, something like this. We're going to have a crystalline solid at 0 Kelvin. A crystalline solid at 0 Kelvin has 0 entropy. Right? Technically, that's not possible, right? Because remember, you can't be at absolute 0, right? You can't be at absolute 0. All molecular motion would cease, right? That's impossible due to quantum mechanics. So anyway, we have a perfect crystalline solid. So it's at 0, right, theoretically. We start heating it up. As we're heating it up, what's happening? Your entropy is increasing. Why is your entropy increasing? Because as you heat your solid, what happens? You're at 0 Kelvin, there's no motion. Everything's solid, right? As you heat it up, what happens? The molecules start to vibrate in different ways. As they vibrate, they have more states available because they're moving. When it's not moving, right, there's only one state available. Then the entropy is 0. As it heats up, it's moving more and more and more. As it heats up more, the molecules move more, giving more states. Thus, entropy increases. So this is for a solid. Eventually, you're going to reach such a temperature, you're going to have a phase change. And you go from a solid to a liquid. Sorry, my arm hurts when I do that. Anyway, what happens when you get here? we're we're still adding energy, right? What happens during a phase change? Your temperature does not change during a phase change, correct? Where's that energy going? It's going into breaking those bonds that are in the solid. The molecular bonds are in the solid. But our entropy is still increasing. Actually, let me use this. So again, here you're going from a solid to a liquid, right? Your temperature does not increase when you go through a phase change. However, what's happening? You have more states available, so your entropy is still increasing as you go from a solid to a liquid. Instead of the molecules being held rigidly together, pretty soon they can all move past one another. Now you keep heating the liquid, you're heating up the liquid. What happens? The molecules are vibrating faster and faster and faster. Again, more states are available. Entropy keeps increasing until you again get to liquid to a gas. What happens again during a phase change? Your temperature doesn't change, right? Your molecules are sliding past one another. Eventually they're getting enough energy to fly off, right? Once they fly off, here you're changing to a gas, more and more flying off. Once you get them all into the room, they're all separated now. They're all gas, right? Again, the more energy you add, the more states are available. The faster they're going, the molecules can fly around. So again, your entropy is increasing, right? I hope I made that somewhat clear or understandable. So yeah, I guess delta S greater than 0, entropy is increasing. Delta S less than 0, the entropy is decreasing. Again, you've ordered the system, right? So let's just take a look at a couple more examples. If I'm going to make coffee, right? I have water, I have coffee grounds, right? The entropy, you have a certain entropy. When I make the coffee, I pour the water through the coffee grounds, picks up some of the different coffee molecules, or you want to say caffeine, different things. And what happened? I increased the entropy, right? I increased the entropy by mixing the two. Anytime you mix two systems, two different substances, you're going to increase the entropy because more states are available. If I burn wood, what happens? We got a wood burning or coal burning or whatever. The entropy is increasing, right? You're going from, say, let's just look at, say, a butane lighter. You're going from C4H10 plus O2 to CO2 and H2O. So basically you're going from butane, which would be a liquid, oxygen, and gas, and you'd be going to CO2 and H2O gases, creating more. The entropy is going to increase. The two gases are going to have more freedom of motion than the butane liquid and the oxygen gas. And there's more combinations. But anyway, now let's continue on. We need to know a little bit about entropy because we have to talk about the Gibbs free energy. The Gibbs free energy is important in biochemistry and different chemical reactions, okay? The Gibbs free energy is basically the amount of energy available to do work. Is one of the ways you can think about it, okay? Sorry, I gotta write lower. Gibbs free energy is done with a capital G. Okay? Sorry, I gotta write down here. Our Gibbs free energy, okay, G again is the change in. Sorry, the delta is the final minus the original. God damn it. Sorry, I gotta quit pointing with this arm. Gibbs free energy, remember H, that's enthalpy, right? That's the change in enthalpy. Here's our entropy, right, times delta S, okay? So let's write out what these things are. G, again, is Gibbs free energy, right? That's going to have units of joules, okay? H is the enthalpy. That's also going to have units of joules. T is the temperature. That will be in Kelvin. And S is the entropy. And that has units of joules per Kelvin. Okay? Now remember when we had enthalpy, right? Delta H less than 0 was negative. That meant it was exothermic. Excuse me. Delta H greater than 0 means that it's endothermic. It feel cold, right? You actually feel cold. You're taking heat in. Now delta S here, right? Delta S, if the entropy is increasing, what happens? That's positive, right? But we'd end up with a minus here, okay? If delta S entropy is decreasing, what happens? That's negative, right? Then negative times negative, that'd be a positive, right? Long story short, what am I getting at? Delta G less than 0 is spontaneous. Delta G greater than 0 is non-spontaneous. Right? This is very important, okay? We're not going into a lot of detail here, right? But delta G less than 0 is spontaneous. That means the reaction will automatically happen, right? Delta G greater than 0 is non-spontaneous. That means the reaction will not happen unless we put some energy into it. Real quick example. Delta G is spontaneous, a spontaneous reaction. If we have sodium solid and they mix it with chlorine gas, that delta G would be less than 0, okay? An example of delta G greater than 0 is if you want water to decompose into hydrogen and oxygen, okay, that process, H2O, 2H2O into 4H2, 2O2, is non-spontaneous, okay? How do you make that happen? You have to put energy in. Generally, you have to like run an electric current or something through the water, right? So delta G less than 0 is spontaneous, delta G greater than 0 is non-spontaneous. If I put a little degree symbol on here, okay, what that means is under standard state. Remember standard state? That means 1 atmosphere of pressure and 0 degrees 0 degrees Celsius or 273